So we are still working on the Cauchy's theorem. So we have two. One is Cauchy's integral theorem. So if you have some complex function is analytic inside of the curve C, the theorem says this area domain D, if a function fc is analytic inside of C, then this Cauchy's integral theorem, right? And if Z naught has to be happen to be in the point inside of the Z, then there is the derived theorem or formula called Cauchy's integral formula. Which says this is called the Cauchy's integral formula. And the extension of Cauchy's integral formula is a residue theorem. It's again Cauchy. So can I move on to the next page? I have to add. Yeah. And there's another residue theorem. So integral formula is not a theorem. Actually, it's a byproduct of Cauchy's integral theorem, but Cauchy's residue theorem is also a byproduct of Cauchy's integral formula. So that says there are many poles and C, then this integral pi I sum over k and residue of ck. And this Cauchy's residue theorem is actually a very powerful technique or powerful tool that allows us to compute the very complicated integrals. So they actually provided unprecedented analytic capability to the mathematicians or engineers and scientists about 200 years ago. So our ancestors has a very powerful computing tool, even without the computer. So basic rule is the following: transform real integral into something like this by adding zeros, right? So assuming that you have a very complicated something like fx dx. It's very complicated, AB. And you add some zeros, normally 2 zeros. So 1 0 can be like a big circle, and another 0 can be small circle. The 0 is actually some integral along a big circle and or small circle. So we have done this before, right? So you transform the real integral into the closed complex integral by adding some zeros, which can be either the integral along the big circle or the integral along the small circle. And we have done some examples in previous week, the week before last week. Then this complex integral is, of course, you can use residue theorem. So it's the residue FCK. So we covered 2 examples. One is just inverse tangent C, right? The other one, the example we covered was something like a shark. So I can move on. The real technique is you have some very complicated real integral. Then by ingeniously adding some zeros, maybe 1 or 2 zeros, you can transform it into the complex integral. And then you can evaluate the integral by using that residue theorem. So that's it's a very powerful tool. And let me see. If I have to add into it's more general to say because the example I was going to solve was actually sometimes you may even transform fx into not something modified from fj. So that's more general statement. So this gz is modified fj. The easiest case will be fx taken at z, but sometimes you may do a little bit more, and little bit modified form of FT, so we haven't get there. But let's start with the case. So the first two cases we have done is fx become fz, right? So let me see. I have. Is there any way that I can go back to the note? Let's see. So let's try. So I can give you one example. Okay, we have some integral dx. No. Actually, this is maybe a little bit more complicated, so I can do something simpler. Because sometimes actually, okay, so I was recording the previous lectures, right? So, thank you. So this integral, you have to be a little bit more be ingenious. So fx is x3 plus 1 over 1, right? And the goal is to into something 3z. Which is related to the original integral. So this function is very tricky because at first the lower bound is 0 and upper bound is infinite. And x to the cube is the odd function, right? So we cannot represent. First problem is we cannot extend we cannot do this integral because obviously x cube is odd. So it's not 1/2. And secondly, fc single valued. Previously, we used the multiple valued function to use the contour that includes the 0. So cannot be used. But at least this idea is very intriguing because contour like this allows lower bound 0 to infinite, right? So is there any function? So the goal is to find, so if we can find some function gz which is not single valued and use the above contour above. So we know very simple non-singular, non-multivalued function which gives difference between at this point and this point. That is globe, right? So here, I think apparently So we know that here log x, but here log x exponential 2 pi I is log x plus I 2 pi I, right? I 2 pi I. So if you multiply log to the fx, fz, then you might make this whole integral possible. So let's check that. So set gz is g squared plus 1 ln z. And consider this contour. This is 0, C1, CR, C2. On C1, this integral, infinite to 0, it becomes x cubed plus 1, we have ln x, right? dx. Actually, it's from 0 to infinite. So this is your point x. This is x exponential 2 pi I. Right? So on C1, if we integrate G2, Gz, then it becomes ln x, right? Divided by x3 plus 1. That's C Gz dz. How about C2? C2 Gz dz becomes infinite to 0, right? And everything is the same except ln x become ln x plus 2 pi I, right? dx. So, and poles. So C1 plus C2 becomes C1, C2 is what? 0 to infinite, x3 plus 1 ln x minus 0 to infinite, x3 plus 1 ln x dx minus 2 pi I x3 plus 1 dx, right? So when you add them together, then this cancels each other. And this is actually the original integral we wanted to evaluate. This is I. And how many poles do we have? Poles. Z cubed plus 1 equal to 0. So Z is minus 1 exponential I pi plus 2n pi. So Z is actually exponential 3 over I pi plus 2n pi. So we have 3 poles. C0 is when n is equal to 0. So exponential I pi over 3 C1 exponential I 3 pi over 3 I pi C2 exponential I 5 pi over 3, right? So we have 3 poles. One is here, and here, and here. Z0, Z1, Z2. So you only need to evaluate 3 residues. Very simple, right? Not so difficult. So we're almost there. And of course, zero. And this I will leave a homework. So you can get home. In actual, in quiz or final exam, you have to show that too. So you have to show, you need to show this in quiz or final. So this is important. So that's the reason why I like to leave it as homework. But I can assure you that this 2 will give 0. So you get your homework, and then if I ask this problem, then you fill out that why this is 0. You have to do that. So let's go back to the original problem. I'm tempted to make a copy of that figure, but I'm going to do it again. So, write something. I will get you copy things. You still need to make so. This is our contour, final contour. You have a branch cut, you have a pole, Z0, Z1, Z2. So the original integral is this. So fx is x plus 1 over 1. But we transformed into the following integral for this function. ln z over z cubed plus 1. Then this closed contour C gz dz is simply minus 2 pi I 0 to infinity it turns out to be 2 pi I sum over residue G C0 plus residue GZ1 residue C2. So now we need to evaluate residue. So Z naught, Z1 exponential I pi, Z2 is exponential I 5 pi over 3. And GZ so this is following from NZ over DZ. And some time ago that I gave the formula for evaluating the residue when the function is given by divide the NZ over DZ. So that's very simple. So residue GK is simply T prime ZK and ZK, right? You remember somewhere maybe 2 weeks ago I have done this. So that's very simple. So residue denominator is Z3 plus 1. So the residue GZ0 is simply 3Z0 over ln Z0, right? So this is what? 3 times exponential I pi over 3 times ln exponential I pi is 1, right? ln 1 plus I pi over 3, or I should say exponential I pi over 3 is simply I pi over 3 times exponential minus I pi over 3 so let's, are you following me? The calculation is not so simple, not so complicated. So even I can remember. So that is I pi over 3, right? Or 3z, yeah, square. So that's 2, right? So 2. Thank you. I could have made a big mistake. This part is minus 2 pi I, right? So continue I pi over 9. What's it I? Cosine pi over 3 minus I sine pi over 3. So, yes? That has to be 2. So, this is all sine, tan, cosine, right? Just from your high school days. So 2 pi over 3. 2 pi over 3 is here, right? So cosine is negative, sine is positive. So it will be pi over 3 minus 1/2 minus I square root of 3 over 2. It is 9. Sorry. So that's residue Z0. Residue Z1 is 3 times exponential I 2 pi, right? ln exponential I pi. That's correct, right? So this is 3 over I pi times 1. And residue GZ2 is 3, Z2 was I pi over 3, C1 was exponential I pi, C2 is exponential I 5 pi over 3, right? So that's so we have ln exponential I 5 pi over 3, 3 times exponential I 10 pi over 3. 10 pi over 3 is same as 4 pi over 3, right? Because we can subtract 2 pi and I 5 pi over 3. So this is 9 I pi over 5 cosine 3 4 pi minus I sine 3 over 4 pi. And so this is a third quadrant where this is negative, this is negative. So it becomes 9 I 5 pi minus 1/2 plus I square root of 3 over 2. So now let's add them together. So residue GZ0 plus residue GZ1 residue GZ2. You just need to add them together. You just need some patience. So it's okay. Let's use pi over 9 as a common factor. I pi over 9. Then minus 1/2 minus I square root of 2 plus G1 gives 3, right? This is 3 pi over 3. So if we comment with the common factor of 9, this becomes just 3. And we have 5 over 2 plus I 5 over 2 square root of 3. Let's check this. How about this, this, and this? 3 minus 1/2 minus 5 minus 2. 0, right? So those become 0. So it simply become, we have I, so become I pi over 9 times 2 over 4 I square root of 3 is minus 9 over 2 pi square root of 3, right? pi times 2 over 2 is 2 square root of 3 and I become minus. So that remember this value and let's go back. Yeah. So we have closed contour integral of gz dz has become minus 2 pi I is 2 pi I times, do you remember the value? Minus 9 2 pi square root of 3, right? Let me see. So this cancels each other and minus 9 cancels each other. So I becomes simply 2 pi over 9 square root of 3. So also pi is appearing everywhere. But isn't it nice that we can get this complicated integral? Before I move on next problem, maybe you can take a break for a few minutes. 이거는 그냥 목을 안 쓰고 이거 영어 보여줄게요.
이거 그때 한 거는 이렇게 알고 무한대로 보내면 영어로 가가지고 얘기가 하는데 적은 거 같은 경우는
앞에 빼줄 거야. 기수가 왜 이게 로우 타임 로가 영어로 하면
그냥 얘를 그냥 한없이 작게 해서
앞에 그 이걸로 생각을
근데 썸은 아니지. 아,
이거를 영어로 보내주면
썸이 아니라 그냥 아리거나 로겠지.
그리고 이 여기 사이에 이거를 잡았고
네.
이걸 이제 영어로 보내줄게요.
보내면 이거랑 이거랑 서로 섞여.
근데 이거를 제가 그 C 아래에 C 5가 있어요. C 5를 이렇게 보는 거 아니에요?
실론이 요거지. 맞아요.
R라고 하시는
그렇지.
U가 0으로 갔는데 앞에 R 같은 거는 이게 무한대로 가니까 R분의 파이 이런 것도 아니고 무한대가 되면 얘는 농도를 보기가 쉬운데
이거는 이렇게 B가 로에 I 피타에 있을 타에 이게 로가 조금 나빠.
그냥 U가 0으로 가니까
0이다.
그게 쉽더라고요.
할 거예요. 자, 분모가 큰 게
네, 맞아요. 맞긴 한데 섹터가 2분의 8일 때 예외가 생겨요. 그래서 그것 때문에 섹터가 2분의 8이면 얘가 마이너스 1이 되니까 얘가 i 제곱하기 1의 제수가 나오니까 왼쪽에 높아야 되는
아니 원이 큰가 없어. 그러니까 이렇게 하면 마이너스 R제곱보다 플러스 1이잖아. 이거보다는 이거보다는 이게 높잖아. 이게 마이너스여도 마이너스 R제곱보다는 마이너스 R제곱보다 역수를 취하면 마이너스 어떤 취한다고 치면 영어니까 이게 좀 알이
아니 큰 값이었어 이게 생각한다고 치면 이거 수동하고
내가 보여주고 싶은 거는 0이 0으로 작아요. 이거 걱정하면 돼요. 너무 괜찮죠?
그럼 괜찮을 것 같아요. 저도 저거 똑같은 거
네가 되세요.
제 파이 들어가지고
그러니까 나는 부등식을 썼는데 R이 굉장히 커지면 그냥 이렇게 쓰면 되는 거예요. 1에 비해서 이게 훨씬 크니까 쓸 수 있으니까
아래 무조건 1보다 크다고 했잖아요.
R을 무한대로 보낼 거니까. 이게 유튜브가 올려서 코드 여기서 썼죠. 무한대 그렇네. 코드 이렇게 보여요.
네네.
여기서 0이잖아.
네.
남는 진짜 텀이 낫겠지. 아무튼데 얘는 어차피 D를 줄 수도 있는 게
네네.
이게 여기서 자, 동호에서 이라고 이렇게 그래도 이거는 그냥 이렇게 이거는 영역이 이쪽이 퍼센트니까
계속 하고 있어 맞아.
왜냐면 이거는 이때 일을 버리면 안 되지. 이것이 작은 거. 루트를 영어로 하니까 영어.
이게 결국에는 이거를 다 경로대로 풀어주면 값이 이게 나오거든요.
그렇죠. 예.
근데 교수님이 이 레지듀 시어링을 해주실 때 FII하고 여기 이 값을 이 녀석으로
해야 되는 거예요.
근데 이 녀석
이게 G가 되는 거지. 얘는 F.
제가 생각하기에는 얘에서 다시 얘를 다시 레지듀 시어링을 만들어서
그게 안 돼서 하는 거예요. 근데 할 수도 있고 이렇게 잡으면 돼요.
이게 약간 트릭 같은 거
네, 트릭이죠.
잡아주거든요.
네, 트릭이죠. I guess I was recording everything. I guess that's okay because it's a Q&A. So Q&A was also recorded, so maybe good for your understanding eventually. So that's your ultimate integral. So you can calculate this integral, and then I think you learn most of the complex variable that I wanted to convey. So fc. So let's consider this function fc. So in this case, fc is 1/2 1 plus c square tz. Looks extremely complicated, isn't it? Right. So let's consider a simple function. First, for general case. So before actually we do this, I'm going to consider this. So this is basically the same as a minus z, b minus c. let's consider the following. So we have some one point A, this is B, point C. Then z minus a can be written as r1 exponential I theta 1. Z minus b is r2 exponential I theta 2, right? So z minus a, z minus b is r1, r2 exponential I theta 1 plus theta 2. So z minus a, z minus b f is square root of r1, r2 exponential I theta 1 plus theta 2 divided by 2. So that is your gz. Absolute value of gz is actually square root of r1, r2. So I'm going to do some analysis. So A, this is B. So we are going to consider six different regions. 3, 4, 5, 6. Z minus a is r1 exponential I theta 1. Z minus b is r2 exponential I theta 2. So in region 1, in this region 1, so see 1, 2, 3 is just above the x-axis, and 4, 5, 6 is below the x-axis. So here 1, theta 1 is equal to 0, theta 2 is equal to 0, right? Theta 2. So 1, 2, 3 is just above the x-axis. 4, 5, 6 just below the x-axis. So we are going to set one, 2, 3, 4, 5, 6. So this is your point here. Then the angle from B is 0, right? And here is 0, 2. So theta 1, theta 2 is 0. How about here, at this point? Theta 1 is 0, but theta 2 is pi. Theta 1 is 0, theta 2 is pi. Because the angle here, if you take a look from here, then you have to go pi, right? And in this region, both theta 1 and theta 2 are pi. Theta 1, theta 2 is pi. How about this below? Same, right? Here, theta 1 is pi, theta 2 is pi. How about 5? This is different because in this region, the angle from here is still pi, right? But from A, theta 1 is become 2 pi. Theta 1 is 2 pi. Theta 2 is pi. And region 6, of course, both angles are 2 pi. Theta 1 is theta 2 is 2 pi. Oh, so we calculate theta 1 over theta 2 in 6 different regions. One, 2, 3, 4, 5, 6. So that is 0. This is pi over 2. 3 is pi. 4 is pi. 6 is 3 pi over 2. It's 2 pi. This is the behavior of G. Because GZ. Square root of R1, R2 times exponential theta 1 plus theta 2. So now, remember that. So theta 2, theta 1 plus theta 2 is behaving like this way. One, 2, 3, 4, 5, 6. So that angle is 0, pi over 2. Pi, pi, 3 pi over 2, 2 pi. That's the region A, B. So this is 1, 2, 3, 4, 5, 6. So GZ becomes GZ square root of R1, R2. Exponential I theta 1 plus theta 2 over 2 is absolute value of GZ times exponential I theta 1 plus theta 2. So your function is changing, behaving very strangely. So in this region, we have simply GZ, I times GZ, minus GZ, minus GZ, minus I times GZ, GZ. So you have to remember that. So simply GZ is this Z minus A, Z minus B, 2D1 half. So that's the behavior of this function along these 6 different regions. So you can still follow me, right? not that difficult. So the real difficulty is the following. You need to copy. So this function 3 and 4 we have to minus sign, right? Minus, minus. So from this become I. So you see, let's go back to this integral. And we take the contour, so dx, so fc C1, C2, 0, C3, C4, and of course this CR. And we have two poles, right? I minus I. So on C1, minus infinite to minus 1. This is pi, so we have minus sign. Plus C4 absolute value of this. There is a reason I put the absolute value. This is minus 1 to minus infinite. Again, minus 1 dx. But obviously C1 plus C4 is 0, right? C1 FC dz, C4 FC dz equal to 0. And we need to evaluate C3 and C4. C2, C2, we have I, right? We have I, dx, and C3 is 1 to minus 1 dx minus I 1 plus x squared. So if we add them together, what do we have? C2 plus C3. C2 plus C3. Simply 2 by dx. Simply 2 by I. And as homework, we need to add 2 zeros, right? So where was I? This is I over 2, right? So closed integral actually 2I over I this is homework. But you have to show that in the exam. So this becomes actually 2 over I times I is 2 pi I residue f exponential I pi over 2 residue f exponential 3 pi over 2I. Of course, fz is z squared plus 1 square root of 1 minus z squared, right? So f residue f exponential I pi over 2 is 2I, right? 2I times this one is square root of 2. See, 2z. Times I. Not okay. So actually it has to be 1/2. So we have I. So minus 2 square root of 2. And residue f exponential I is 3 pi over 2 is this become minus 2I, but the evaluation of this 1/2 function gives minus I. So minus I square root of 2 is again minus 2 square root of 2. So if you add them together, residue f exponential I pi over 2 residue exponential I 3 pi over 2 gives minus 1 over square root of 2. So if we go back, oops, sorry. Summation over 2 is minus square root of 2. So closed integral actually becomes 2I over I is 2 pi I times residue f exponential I pi over 2, residue f exponential I 3 pi over 2. So I becomes pi times I is minus 1, right? And we have minus 1 over square root of 2. So pi over square root of 2. It's amazing, right? So we can do this. And this all comes from the analysis of this function, c minus a, c minus b to the power f in 6 different regions. Or so maybe you can try to do this. Maybe A, B. A minus x, B minus x, AB minus BX minus AX. Right? So a bit more complicated form. Maybe c square. And b is greater than 0, a is less than 0. So we can solve this equation, right? So more. So this is about the complex analysis that I was going to cover in this semester. And we have half an hour. So let's change the topic and just do a little bit. Complex analysis 5. And maybe I have to change it into Fourier, but Fourier analysis 1. Then I can start with 2 next time. And okay, so I was not recording during the change of project. So we are going to into a new area called the Fourier analysis. So Joseph Fourier, the discoverer or inventor of Fourier series, was also the French mathematician of early 18th century. And Napoleon also gave him another problem. So Napoleon was an artillery officer, right? Artillery is 포병. And at the time, artillery was a very important piece of weapon during the conflict at the time in Europe. The problem was the metallurgy technology was not mature enough, so after certain firing, something like that happens. So the cannon explodes after certain firing, like maybe 100 times. So Napoleon asked Joseph Fourier to investigate. And what was the reason? And he found that it was the temperature accumulation in a certain region. So the artillery using explosives, black powder, and then it's very hot, right? So after firing, it become hot. But some part of the cannon become more hot than others. And what happens? If the metal become hot, then it becomes weak, right? So certain weakness point become the center for the explosion. So where this region is weak, then there is enormous pressure built inside of the cannon when you fire. But if it cannot withstand that pressure, it becomes exploding. So he was trying to find out how to model the temperature distribution of the cannon as a time function. So he was changing something like this. So actually it was temperature. So after certain temperature, then the part of the region becomes different. So he considered that the problem is something like a periodic function of time. So each point in the cannon, the temperature is a function of T, and it becomes repeating itself. So temperature distribution is something like that. So this is T, this is the temperature. When you fire, the temperature rises. And between the firing, the temperature is lowering, right? So he discovered that by maintaining the firing rate below certain temperature, then you can use the cannon safely. So this is some critical temperature. If we fire very rapidly, what happens? Temperature can build up, right? So it becomes something like that, Tc. Then at this point, the cannon will explode. So he was trying to find out this problem, and then what is the period that you can safely fire the cannon. Very nice, right? So he was, so basically this problem, we call the periodic function. So mathematically formulating the temperature function as a periodic function of T, and he discovered the optimum period that you can safely fire the cannon and without breaking the barrel itself. So before we study the general problem, we can safely study a simple function. Before we consider general period, we can consider some specific case of a periodic function, say 2 pi, and how to represent this function. And we already know that some function which has a period of 2 pi, that is sine and cosine, right? So Joseph Fourier actually tried to expand some function of a cosine n pi then obviously cosine n t plus 2 pi is cosine nt plus 2n pi, same as cosine nt, right? And sine n t plus 2 pi is sine nt plus 2n pi sine nt. So the question is, if you know the functional form, then find a, an, bn. It's a basic problem of a Fourier analysis. So simple. What if we integrate from this ft dt? It's a times minus pi pi dt plus an pi cosine nt dt plus bn sine nt dt. This is very easy to evaluate, right? If we evaluate 1 from minus pi to pi, what do you get? 2 pi. How about this? Any cosine nt function, if we integrate from minus pi to pi, we get 0. We get 0. So at least we can find out the first coefficient a, say a0. So A0 is simply, okay, I'll let you copy this. So A0 is 1 over 2 pi minus pi to pi ft dt. How about if we multiply ft by cosine mt, and then you integrate minus pi to pi dt. Then this is again A0 times minus pi to pi cosine mt dt plus n equal to 1 to infinite an minus pi to pi cosine nt cosine mt dt plus. So this is basically the integration you have done in high school days. Minus pi to pi sine nt sine cosine mt dt. So this part is easy. This is simply 0, right? Cosine mt cosine nt integral is okay, I will let you copy. I mean, if this part. So we also need to do this part. So now we know that this is pi times delta nm, right? Sine, cosine. Well, what is this? Did I do something wrong? This one. This is always 0. So before I do this, cosine nt, cosine mt. Coco, right? So, do you remember this formula? 1/2 cosine n plus nt. That's you learned in high school days. Cosine A, cosine B is coco, right? Coco sasa. I mean, cosine A plus B is cosine A, cosine B minus sine A, sine B. That, you know, in high school days, minus B is cosine A, cosine B plus sine A, sine B. So if you add them together, then you get the above formula. So this integral, minus pi to pi, cosine nt, cosine mt dt, is 1/2 cosine n plus m t dt plus 1/2 cosine n minus m dt. This part of the integral is always now n m was greater than 1. So this part of the integral is always 0, right? How about this? When n is equal to m, then the argument of cosine is 0, and cosine 0 is 1, so it's 2 pi. And n and m are different, then it is of course 0. So this is 2 pi zero otherwise. So this integral can be written as pi times delta nm. Right? So this is canonical delta. And but also we have to do sine part. If you go back to this, so this is 0. Oh, no, this is not. Sorry. Not this one, but sine n pi, cosine n pi, nx, sorry, nt, dt. Sasa, right? Kosa, sasa. So this must be 1/2 sine n plus m t dt plus sine n minus m t dt. So it can be seen as the following. Sine a plus b is sine a cosine b plus cosine a sine b. Sine a minus b is sine a cosine b minus cosine a sine b. So sine a cosine b is 1/2. So, but this is always 0, right? This. When n and m are same, then this is 0. But sine 0 is 0, right? When n and m are different, then of course this is 0. So this is always 0. So we have ft cosine mt dt is pi am, or 1/pi ft cosine mt dt. And using the same analysis, we can show that Pm sine mt dt, and I like to do this as homework. But I'm going to derive this, show this in next class. But since we are running out of time, I'd like to do the second part as homework. So if it is okay with you, I'd like to stop today and continue next week. So make sure that I turn off the record.